Hi, my name is Jalen, and today I'll be presenting joint work with my collaborators at Microsoft Research and MIT. And I'll start by dissecting the title of our paper. So our work deals with cloud analytics workloads, meaning OLAP-style workloads that you might run on cloud analytics services like Amazon Redshift, Google BigQuery, Azure Synapse, or Snowflake. But even though our paper focuses on cloud services, the techniques we describe are also useful for data analytics services more broadly. So for example, you can apply our techniques on big data tools like Spark and on-premise data warehouses like Vertica. Now to explain what I mean by data layouts, I'll use a running example. So let's say we're using Azure Synapse and we load this table, where the three columns are date, price, and quantity, and each row represents some order made by a customer. So to physically store this table, Synapse will first horizontally partition the table into large blocks, each of which typically contains hundreds of thousands or millions of rows. Then each of these blocks will be persisted in a compressed columnar format on cloud storage. Now let's say the user wants to run a query like shown here. Select the average price from this table, where the date is between January 10th and 20th, 2020. So this query will be sent to a compute node, which will process the query by reading each of the data blocks from remote cloud storage. Now, reading a block is actually quite expensive due to both I/O costs and computational costs. So we would like to avoid reading blocks that are not relevant to the user's query. And one very common technique that cloud analytics services use to skip irrelevant blocks is to maintain zone maps for each block. So zone maps are these compact pieces of metadata that store the minimum and maximum value for each column over all rows in a particular block. So for example, this very first zone map that I'm showing at the top indicates that rows in block 1 have a minimum date of January 1st, 2020, and a maximum date of February 29th, 2020. Now, using these zone maps, the compute node can process this user query by only reading block 1. And that's because the zone maps indicate that blocks 2 and 3 only contain rows after March. So data in those blocks are not relevant to the user's query. On the other hand, if the user runs a second query with a filter over the price column, as I've shown here in orange, the zone maps are unable to help us skip any blocks because all three blocks contain data that's relevant to the query. So the key insight from this example is that the effectiveness of the zone maps and the degree to which we can skip blocks really depends on how we cluster rows into blocks. So in other words, query performance really depends on the data layout. So the key challenge here is how do we create data layouts that minimize the number of blocks that we have to read during query execution? So there are a variety of existing techniques for defining a data layout. The most common technique is to sort the data by a particular column, such as the date column. But as we just saw in the previous example, this technique might not be super effective if queries filter on multiple different columns. As a result, many systems also support multi-column sort orders, for example, based on compound or composite sort keys, and some systems have also begun to support interleaved sort keys based on the multi-dimensional Z order. And even more recently, there's been a lot of research on what I'll call instance-optimized data layouts, where the key idea behind this line of work is to automatically optimize the data layout, often using machine learning, in order to achieve high performance for a particular data set and workload. Now, unfortunately, one significant limitation of all of these techniques is that they only define the layout for a single table at a time, even though real-world analytics obviously happens over data sets with many different tables. So in our paper, we address this limitation by introducing MTO, which is our multi-table layout optimizer. So MTO is built for multi-table datasets. For example, datasets where tables are connected in a star or snowflake schema that you would typically find in a data warehouse. And MTO targets workloads that include join queries over multiple tables, like in the example that I'm showing in the bottom right. Now, unlike existing techniques that optimize each table's layout independently, MTO is able to jointly optimize the data layout for all tables simultaneously, which leads to potentially significant reductions in both block accesses and overall query time. And as I'll explain throughout the rest of this talk, the key idea behind MTO is to take advantage of something we call sideways information passing, and we do this using a construct called join-induced predicates. So before I dive into the nitty-gritty details of our algorithms, I first want to provide some high-level intuition behind MTO. And I'll start by describing QD-tree, which is an existing method for creating instance-optimized data layouts on single tables. So the original QD tree paper was published at last year's SIGMOD, and we actually use QD tree as a fundamental building block in MTO. So the intuition behind QD tree is to customize the data layout to a given query workload in order to reduce the number of blocks that we have to access when running that workload. So for example, consider a workload consisting of a single query, as I've shown here, which has two predicates, as I've highlighted in green. Now, intuitively, what we want to do is to create a data layout where the relevant rows to this query are separated from the irrelevant rows. So let's take all the rows from this table that satisfy the predicate price greater than 10 and put them in block 1. And let's put all the remaining rows in block 2. So now during query processing for this particular query, we only need to access block 1 because we know that block 2 doesn't contain any relevant rows. And we can actually apply this intuition again by further partitioning the rows in block 1, this time based on whether they satisfy the other predicate, country in USA or Canada. So now during query processing, we only need to read block 1 and we can skip blocks 2 and 3. So we've essentially built a decision tree, and we call this a QD tree, where each leaf node of the QD tree represents a data block, and each inner node contains a predicate that we call a cut, because it cuts the data space in two. So this QD tree defines the data layout for this table, because each row in the table can now be assigned to a block by traversing down the QD tree. So for example, consider the record shown here. To assign this record to a block, we first start at the QD tree's root node, and we ask whether the record satisfies the cut. So the record has a price of 15, and the cut asks if the price is greater than 10, so the cut is satisfied. And we traverse down the left branch, which represents yes. Now at this next node, we again ask whether the record satisfies the cut. The record's country is Germany, but the cut asks if the country is USA or Canada. So the cut is not satisfied, and we traverse down the right branch, which represents no. So in the end, this record is assigned to block 2. Now, when executing queries, the engine needs to determine which blocks to read and which blocks can be skipped. And there are essentially two ways to do this. The first way is to build a zone map for each block, just like in the example at the beginning of this talk. And now for any incoming query, the zone maps will tell us if it's safe to skip a block. But another way to determine the blocks that we need to read is to actually use the QD tree directly. So for example, consider the query that I'm showing here on the right. To figure out which blocks this query needs to read, we start at the root node. And we ask, does this query want rows that satisfy the cut? Or does it want rows that do not satisfy the cut? Or does it want both? And the answer is that this query wants both, because the query does not filter over price. And therefore, we traverse down both branches. Now, in the left child, we again ask whether the query wants rows that satisfy or don't satisfy the cut, or both. And in this case, the query only wants rows where the country is USA. So we only go down the left branch. So now we know that the query must access blocks 1 and 3. So in the end, there are these two ways of determining which blocks to skip. The first being using zone maps, and the second being to use QD tree directly. And it turns out we can actually use them together, meaning if the zone map method tells us to read one set of blocks, and the QD tree method tells us to read another set of blocks, what we have to do is read the intersection of those two sets. So now I've told you how the QD tree is used, but how is it actually constructed? It turns out there are actually a couple of different algorithms for automatically constructing a QD tree, given a table in the query workload. You can refer to our paper for more details, but the key intuition to remember is that in order to minimize the number of blocks accessed when running a workload, we should define the layout using the predicates that appear in the workload. So in this example, you'll notice that the two cuts in the QD tree are the same two predicates highlighted in green that appeared in the original query. So one implication of this intuition is that before we even construct a QD tree, we need to first extract all the unique predicates that appear in the query workload. And I'll come back to this point later in the talk. All right, so I just described how QD tree defines a data layout that's optimized for a particular workload on a single table. So now I'll provide intuition for how to optimize data layouts in the multi-table setting. So again, the goal is for a particular workload and multi-table dataset to minimize the total number of blocks accessed when running that workload. So as an example, let's say that each block contains 1 million rows. And let's say that we have a data set with two tables where table A has 1 million rows and table B has 8 million rows. So table A consists of 1 block, and table B consists of 8 blocks. Now let's say we expect to execute a workload of queries similar to the one that I've written here. Select count star from A and B, where A and B are joined on some common key, and A.x less than 100 and B.y greater than 200. So let's consider how a database admin might manually set each table's layout independently. So first off, all of table A's records will fall in the same block. So the layout for table A doesn't matter. It's always going to be red. But the layout for table B's 8 blocks does matter. So the database admin might notice that the query's filter includes this highlighted predicate on column B.y. So the admin might decide to sort table B's data by column Y. And as a result, the first 4 blocks contain rows where Y is greater than 200. And so during query processing, the execution engine will use zone maps to skip the latter 4 blocks. Now, if instead of manually setting a sort column, the admin had built a QD tree on table B, the resulting layout would be pretty similar to the one I've shown here, because there's essentially no better way to construct a layout if we only use this highlighted green predicate. So this, of course, begs the question, can we use the other predicate that appears in the query, which I've now highlighted in orange, to achieve even more block skipping on table B? So at first glance, the answer seems to be no, because the orange predicate is over table A. But if we think a little harder, it turns out that the orange predicate can actually be useful. And the idea is this. When we execute the query, after we join tables A and B, we know that any rows of the joined relation that do not satisfy the orange predicate are not relevant. Therefore, the rows in table B that produce irrelevant records when joined with A are themselves irrelevant. So, using this intuition, to further reduce the number of blocks that we read from table B, we group together the rows of B based on whether joining with A would produce relevant records. So the first block of table B contains rows that satisfy the green predicate and that would satisfy the orange predicate if the row were joined with table A. And so now the execution engine only needs to read the first block from table B, because all relevant records are located in the first block, and all records in the next 3 blocks would be irrelevant to the query anyway if they were joined with table A. So by incorporating this extra orange predicate into the data layout, we've reduced the number of table B's blocks accessed from 4 down to 1. So the key intuition behind this example is that if table A joins with table B, we can use the predicates from table A to help define the layout on table B, and vice versa. And so this is what we mean by sideways information passing, because we are passing predicate information from one table to another sideways through joins. And in fact, we can pass through multiple joins. So for example, if table A joins with B, joins with C, we can actually pass predicates all the way from A to C. Okay, so at this point, you already understand essentially all of the key ideas behind our paper. And the rest of this talk will just cover the details of how we use this intuition to build MTO. So here's the high-level MTO workflow. First, in an offline phase, the MTO optimization algorithm takes a multi-table dataset and a sample of the past query workload as input and creates one QD tree per table, each of which will determine the data layout for one table in the dataset. Then MTO uses the QD trees to assign rows to blocks for each table, then stores these blocks on cloud storage. And then at query execution time, MTO uses the QD tree for each table to determine which blocks need to be accessed from cloud storage and which blocks can be skipped. So now I'll describe MTO's optimization algorithm in more detail. So we start with a query workload and a dataset. And in this example, the dataset has 2 tables, A and B. And the first step is to extract all the predicates that appear in the query workload, which we're going to use as cuts to build the QD trees for each table. So in this example, we'll focus on the one specific query that I've written here. The process will be repeated for every query in the workload. So there are 2 obvious predicates in this query. The first is A.x less than 100, which affects table A. And then there's B.y greater than 200, which affects table B. However, we can use our intuition about sideways information passing to artificially induce 2 extra predicates. So first, we can use the predicate B.y greater than 200 to induce a predicate over the key column of table A. And we can do something similar for table B. So we call these join-induced predicates. And you'll notice that these join-induced predicates each include a subquery. So we can actually evaluate the subquery to produce a more literal form of the join-induced predicate, which makes it simpler to determine whether a row satisfies the predicate. Now, the next step is to feed all of these extracted predicates into the QD tree construction algorithm, which outputs one QD tree per table, and these QD trees collectively determine the multi-table data layout. So now zooming back out to the high-level workflow, I just described the offline optimization algorithm, which produces the multi-table data layout. So now I'm going to describe how during online query execution, we use the QD trees for each table to determine which blocks to read from block storage. So let's say the user runs a query like the one I've shown here. So MTO will determine the blocks that need to be accessed for each table by using each table's QD tree. So in this example, I'm just going to show how MTO determines the blocks to read for table B using table B's QD tree. But you'll notice that this query also hits table A, so we would apply the same procedure to table A's QD tree to determine which blocks to read from table A. So here in table B, we start from the QD tree's root. And like before, we ask whether the query wants rows that satisfy the cut or don't satisfy the cut, or both. So in this case, the query contains the filter b.y greater than 300, so it only wants rows satisfying the cut. So we only traverse down the left branch, which represents yes. Now we reach a QD tree node with a join induced cut. So the cut asks whether our query wants rows of B that join with rows of A that satisfy A.x less than 100, or rows that don't satisfy that property, or both. And in this case, the query contains the filter A.x greater than 200, so it only wants rows not satisfying the cut. So we only traverse down the right branch, and we conclude that for table B, this query only needs to read block 1. All right, so now that I've covered the core workflow for MTO, I'll briefly mention a couple of practical challenges that we also have to address. So one big challenge is how do we adapt our data layout in the presence of changing workloads and datasets? And this is actually a challenge that existing data layout methods for single tables also face. So, and the problem here is that it's often impractical to completely re-optimize the data layout every single time the workload or dataset changes. So we came up with a dynamic programming algorithm that efficiently identifies the blocks that would benefit most from re-optimization, and we only re-optimize the data layout for that subset of blocks. Now, another practical challenge is how do we prevent optimization time from becoming prohibitively long when scaling to larger datasets? So we did this by optimizing based on a sample of the data. But this actually created an additional challenge of dealing with the well-known phenomenon that the join of two uniform samples has quadratically fewer tuples than a sample of the original join. So we adopt some new techniques to account for this effect during optimization. So you can refer to our paper for more details on these techniques. Now, in terms of results, we evaluated MTO both in simulation and on Azure Synapse, which we call Cloud DW in our plots. And we used 3 well-known analytics benchmarks, namely the star schema benchmark, TBCH, and TBCDS. And we compared MTO, shown in red, against a couple different baselines. First, a manually tuned baseline where each table is laid out using a sort column, shown in gray and yellow, as well as a baseline in which a QD tree is built independently for each table without sideways information passing. And that's shown in blue and purple. And overall, MTO leads to up to 75% reduction in query time compared to the alternative data layouts. Now, some queries benefit more from MTO than others. Here I'm showing 3 different plots, one for each workload, and the x-axis is the reduction in query time achieved by MTO compared to the alternatives. So it's better to be towards the right. And each point along the curves represents a different query. So you'll notice that on the star schema benchmark, all queries achieve positive query time reductions from MTO's layout, whereas only about 50% of TBCH queries benefit from MTO, and around 75% of TBCDS queries benefit. So a natural question to ask is, under what scenarios does MTO actually provide benefits? So we did a micro-study where we manually clustered the TBCH query templates into types based on various query characteristics. And we analyzed MTO's impact on each query type. So you can find more details in the paper, but the overall intuition is exactly what you might expect. MTO provides the most benefit for join queries that have selective filters over non-sort columns, whereas it provides the least benefit for single table queries or join queries with non-selective filters. So in our paper, you'll also find experiments on optimization time, dynamic workloads and data, and scalability. So to summarize, reading blocks from cloud storage is a dominant cost in cloud analytic services. So the data layout really affects query performance. Prior work optimizes data layouts for single tables at a time, whereas our work, MTO, optimizes data layouts for multi-table datasets. And the way we do this is to take advantage of sideways information passing during optimization. So if you're interested in learning more about the research we're doing at MIT, feel free to check out our blog. I've put the link in the slide. Thanks.